So let me introduce non-negative matrix factorization. For most researchers and students, the problem we have is we think there is a statistical technique that we use to get to the result, but it actually works the other way. We use a certain technique because it makes our conceptual understanding of a certain problem more clear. So in short, the origin story is we've seen this facial recognition pattern software that's used by spy agencies, or if you can find to search how the large language models work. If you have certain words from a lot of paragraphs, you want to pull them together. So that's the basics of this technique. Non-negative matrix factorization is basically, the idea is there is a perception of a whole and there is a perception of the parts. The parts make the whole, and that's what we are trying to understand in this technique, right? So the idea is to understand the core basics of it. Let's deal with the mathematics and then go to how to do it in real time. We have the data matrix, which is the site on the rows, and you have your chemical species across. What we are trying to make in non-negative matrix factorization is those two other matrices. First, we are constructing sites versus number of factors, and the second is factors versus species. When you multiply these two matrices together, we should get our original matrix. So our job is to create one W matrix and one H matrix, and see if they multiply together, we closely get to our original values. That's all. So what mathematically we are doing is, we are trying to minimize, if you see that the formula there, V is our original matrix. V minus the multiplication of WH gives you the minimized error value, and we are trying to get to the least error value. That's what we will be doing in the calculation. The previous steps include how to do that, get to that calculation is this simple formula. The H matrix, how to construct it, W matrix, how to construct it. The best way to understand a statistical concept is to take a smaller portion of the data, handwrite your equations and get to the results so that you can extrapolate that anywhere you want. Let's take, for example, a small 3 by 3 matrix. Like I said, if we have to create a 3 by 3 matrix, the matrix you're dividing should be 3 cross 2 and 2 cross 3, right? That's how the matrix multiplication works. So, do you see this? W0 is the random value. So like I said, our job is to randomly create a W matrix and a H matrix. When you do it in hand, it looks difficult, but now we have computers, you can generate as many random numbers you want. So the W0 and H0 you see there is a random number. So I use this formula here. W0 transpose multiplied by my V matrix gives you my numerator. Then the denominator is again W0 transpose multiplied by W0 and H0, right? It's simple matrix multiplication. We get this component, and from there, right? So we get this matrix first. It's a simple matrix multiplication. Like first you take this row and you take this column, multiply first number, second number on the second row, third number on the third row, right? And you get this 7.2 here and that's 7.2 here. When you finish this, we get to this equation, right? We end up getting the W1. This is your first iteration. What happens in the second iteration? Now we have W1 and H1, right? You move and iterate. So that's what the iteration means here. The two things that you have to remember is the seed run and your iterations. Say for example, I do 30 seed runs. What does it mean? It means I have 30 different starting points. Like I said, this is our first number, right? This number can be anything. This matrix can be any number. So that's what I mean. If I'm doing 30 seed runs, it means I'm using 30 different starting points. What do we mean by iteration is, how long do we repeat this to get the least number of values? You see here, this is my first iteration, error value 4.032, right? This is a formula we have. And you keep doing this iteration, you can go till even any number of iterations. Just that error value is asymptotic in nature. It won't touch the zero, it will just scrape through the zero. So we could, in this smaller data set, we could go till 0.25. And that, to an extent, it recreates your original data. As simple as that. Your original matrix is W, your construction matrix is, original matrix is V, you're constructing W and H, take random values, matrix multiplication, get the error value, keep getting the error values, get to the least error value, voila, the last matrix multiplication step you get is your actual answer. Compare the original versus reconstructed, you get your plots. That's all NMF is. From here on, it is just the code that is available, publicly available. And this is just, I summarized what we are actually doing. So to test it, I've taken a slightly bigger data set from Nirmala's work, soil samples, national data set. We start with 61 sites and 41 congeners analyzed. The most important thing is non-negative in nature. The second important thing is, if we have so many zeros in our data set, the literature says that up to 20 to 30% of null values would actually shift your data significantly. So we are cleaning up the data set as step one. We'll remove the congeners which recorded less than 20% of the sites. So that we get 61 cross 35 matrix, good enough for NMF. And then we do a data consistency check. This is basically arranging your data with proper rows and columns. The Python code is available, I can share it, it's pretty straightforward. Now, like I said, what we are doing is, we started with k values, which is our factor. Now for that bigger data set, I start with 2, right? Why 2? The idea is simple. We have 61 cross 35. The minimum of 61 cross 35 is 35. But you cannot have 35 factors in reality. Think about it. It's just not technically possible. These are sources. We literally have to name them. So we start as least as possible. Why 2 and 8 is, we can see from the elbow plot. The elbow plot is basically the factor and the error reconstruction that we are getting, right? The reconstruction error. As you go down, the reconstruction error is reducing, correct? As we move up the factors, it means more factors are answering and bringing the reconstruction error lower, correct? But check out this area. The drop at which it starts plateauing, that's how we choose number of factors. This is the most important step. This is where researchers have not many papers disclose how they do it, but there's a very definitive step on how it should be done. At a point, it will start plateauing, right? So that's where I've chosen 35.6, 30.6, 14.7, and then again there is a rise. So that's the point, there is a plateauing. So our number of factors would usually lie in the area of the plateau. So let's keep in mind, we'll try between 4 to 7. This is all trial and error. We should not start with a certain answer in mind based on the literature review, which we end up doing when we are forced to get results. That's not the right way to do it. Now second, if you keep pushing ahead, so what happens? I stopped at 8 but still try to continue till 15. What happened? You see it's going asymptotic, but is it meaningful? Can we have 15 sources? Is it possible? You can check it out that it won't make sense after a point. The error keeps reducing, but the meaningful distinction between sources is not possible, right? You cannot name them. You can't have 15 names, at least for the data set that we are dealing with. High factors should not be split correlated congeners or one physical source onto several mathematical factors. That's where the crunch is. So what we did, so the sweet spot is between to test 4 to 8. That's what we are doing now. I did 30 seed runs for 5,000 iterations. Find the runs with lowest concentration error. Now again we see here, the best reconstruction error, the mean reconstruction error. This is the one that tells you, gets us closer to the actual number of factors. If the best construction error and mean construction error are closer and the standard deviation is closer, then it means it could point to your source, the number of factors. As the number C, 7 and 8 also explains the least result, but look at the standard reconstruction error there. The error is going higher, which is what we don't want. So now from that number we have shrunk to 4 to 6. Now next point. We keep doing that 4 to 6 again. That's how we have the Excel file that is downloaded after you do this. You have your H factor, reconstructed value, residuals and W side contributions. Now again, how do you choose 4? We have 4, 5 and 6. How do we choose which one is correct? You can just basically do a cost similarity analysis of 4 sources, 5 sources, 6 sources, right? In each loop you have one source extra. Compare the similarities between each factors. What we are left out with is this. K4F1 is similar to K5F4, right? Like that I've marked all the similar ones. Trap all the dissimilar ones. You will form something like this. You see? Fy F5 in K6 factor does not have a strong one-to-one match. Again, the F2 in K6, which is also present in F5, is not present in F4. We have to check these two things, which is F factor F2 in K6 and Fi in K6. From 4, we can still reproduce it, but the problem is it is still splitting into 2 other new factors. Now we go and check if those 2 factors are real, we keep 6 as a correct number. If not, go back and do 5 and 4. That's all. Don't leave the number of factors to chance. We need evidence at every step to find out why we chose k is equal to 6. That's what we are doing here. Now we will compare. The new K5F3 is not driven by unusual sites. So I get a site type portfolio, right? What site is affected by those 3 new factors that I did not see in 4 number, correct? The new K5 factor is not driven by unusual sites. So which means either I retain the 6 one, I'll find out what is the completely different group. Now I chose k is equal to 6 and ran the ones because I found that the 2 other factors that we get still explains the data. So the measured construction versus mean construction is very good. SSE is good. Root mean square is perfect. Variance explained is the most important parameter. It's 99.4. This gives us the idea that we are going in the right direction. That 6 is actually the right number in this data set. And then from there it's all the reinforcing that k is equal to 6 is the right answer. So how do we reinforce that? We go and do the individual congener analysis. Like I said, the last K5 and K6 actually explains the congeners group that was not explained by the first 4 data set. That's why it tells us that K6 is the right answer. And we see that the improvement percentage of each congener is we are finding out. That is how much, considering that these 2 factors are real, how much is improved in the error value. If the error value is over 57.01, it just means that that factor is real. So now we confirm that whatever we found from the previous step is correct. So this gives you the reconstruction for every single congener. The only problem is with 169. We go back and check what happened to 169. It is because of that one particular site in one particular congener that just shoots up your values. That's what I said. More number of zeros in one particular set of congeners, it's going to drag your data set in that direction. So that's why we go through this level of checking. Ideally, if you want, you can remove 169, but it's really not a good practice. It's good to keep it. It's an important congener and see how it's effective. So this is the plot that you get for sampling site, and this is the manuscript level concentration on the y-axis, congener on the x-axis, and the percentage contribution of each congener on the y-axis. That's it. Thank you.